All right, so this is the next chapter that we're going to take a look at, which is the acid-base application of equilibrium concepts. And we start off with some definitions like we usually do in new chapters. And we try to connect with some of the stuff that you looked at in Chem 200, namely acids and bases. In Chem 200, you guys remember that uh, you worked mostly with Arrhenius's definition of acids and bases, and that just centered around the production of H plus in solution, and anything that increased the concentration of H plus was said to be an acid. Anything that increased the concentration of OH minus was said to be a base. In Chem 201, we're going to mainly use the Bronsted-Lowry definition. Uh, and the Bronsted-Lowry definition centers around the accepting or donating of a proton. So that's H plus. Now, what is H plus? If we look at the nucleus of a hydrogen atom, it only has an electron and a proton in it. So if we take away the electron, then we're just left with a proton. So sometimes we use the name proton to mean H plus. And also when in water, we notice that uh, H plus doesn't really exist all by itself floating around in water. It makes what's called oligomers, or other molecules with groups of water on it. So really H2O hangs on to that H plus, and what we get is the hydronium ion, H3O plus. And then there's other oligomers too, like this one, and so forth. So that's just one more water. But these are not as abundant as the most abundant form of H plus, which is H3O plus. So we usually just stop here and say a proton really exists in aqueous solution as H3O plus. So you'll see it written either way. So you'll have to look out for that. Now, since we know something about equilibrium, um, there's other definitions that come into play. Now, one of the things is that with this Bronsted-Lowry definition, where it centers around the either giving up of a proton or the accepting of a proton, that means that some compounds under this definition can be considered to be a base, and those same compounds under other conditions can be considered to be an acid. Those type of compounds that can do either are called amphoteric. And in this example, in this plate, you see water is an example of an amphoteric species. It can act as an acid or a base, which, begs the question. If someone says, what is water? Is it an acid or a base? Your answer is, I don't know. Tell me how it behaves. So it's really the behavior that you have to look at to define something as being an acid or a base. So in the first example here, we see that water accepts a proton, and so under the Bronsted-Lowry definition, water is a base here. But in the second example, we see that the water gives up a proton, so it's defined as an acid here in that second equation. Any questions on that? All righty, so we're moving right along through some of these initial definitions. Here we have what's called the conjugate acid-base formalism. This also falls out of the analysis of acid-base reactions with equilibrium concepts. So in this formalism, if we look at this reaction right here shown, and we look at the reactants, I have HA, some acid. How do I know it's an acid? Because it fits the Bronsted-Lowry definition of an acid. It's going to donate a proton. And in this case, the other reactant, water, is defined as a base because it's going to accept the proton. But now we know about equilibrium, and we can know that you can look at reactions in either direction, because most reactions don't go to completion. They form some mixture between the reactants and products. When the rate forward equals the rate reverse, we reach equilibrium. So we have the situation where we can look at the products back reacting to make reactants. And if we look at it in terms of that perspective, then we notice that H3O plus is going to give up a proton. And according to Bronsted-Lowry, something that gives up a proton is an acid. And conversely, A minus here is one of the products that if it back reacts to form reactants, it's going to accept a proton and form the HA. So it accepts a proton. According to Bronsted-Lowry, it's a base. Now, because it's on the product side of this equilibrium, it's given the name conjugate. So you can only define the conjugates in terms of the acids and bases, which are given the designation for reactants, and the conjugates are the products. You also know from your equilibrium experience that that's arbitrary. I could have started out with these products as reactants and these reactants as products and drew the equilibrium that way, and then the definitions would have been different, at least the acid and the base versus the conjugate acid and the conjugate base. Now, having said all that, what are conjugate acids and bases? Well, first of all, you have to notice that the acid differs from the base by one proton, and that's in either case here. So I have HA as my generic acid. I know it's going to be an acid because it gives up a proton. What does it make? It makes A minus, so it differs by one proton. The acid differs from the conjugate base by one proton, and that's true for my other pair here, H2O and H3O plus. They differ by one proton. So that's how we can define our acids and bases. Now there's a question down here that see if you can put some stuff together at this point and predict what the pH range for a solution of A minus is. Now, this is some sort of HA is some sort of a generic weak acid. So I'm just going to write that here. HA. So this could be, for example, a weak acid. It could be HF, or it could be an acetic acid, which is CH3CO2H, or some other weak acids. So this is just some weak acid. And I'm going to react that with water, and I can get my equilibrium and so forth, right? But now say I have a solution not of HA, which is a weak acid, and you would expect the pH of this acid in water to be in what range? What range do you think that's going to be? Anybody?
Would it be below 7?
Yeah, why would it be below 7?
Because 7 is neutral or like in the middle, and then anything above that is a base.
Yeah, correct. So you have this type of equilibrium ensuing when you put in some HA in the water. So it comes to equilibrium and you form a little bit of H3O plus. And so that makes the pH go down from 7. So pH would be less than 7 in this case. Correct? I mean, that's what you just said, and that is correct. All right, so consider now, instead of a solution of HA in water, what if we had A minus in water? What would you predict the pH to be in that case? So you got a 33.33% chance of guessing. It's either greater than 7, equal to 7, or less than 7.
Be greater than 7?
Yeah, that's correct. Now, the question is, why would you think this would be greater than 7? Well, first of all, if we were using the analogy with HF, this would be F minus. Okay. First of all, you can recognize that as the conjugate base of HF because we just defined it as a conjugate base. So if we put a base in water, you would expect it to do what a base does according to Bronsted-Lowry, which is to accept a proton. So when I accept a proton, I form HA, and as a result, I have hydroxide. And so I would guess, or like you said, that the pH would be greater than 7 because I'm producing some hydroxide, so the pH is going to go up. Okay, so these conjugate acid-base formalism is important because it helps you not only get a handle on acids, but also bases and their conjugates. So to use equilibrium techniques along with acid-base chemistry, we have to be able to recognize when we're dealing with something that goes to completion, like a first semester general chemistry 200 question, like a limiting reagent problem where we run out of something, versus when we have to apply equilibrium techniques for acids and bases that are weak, that don't go to completion, where there's a mixture of reactants and products. So that's one thing that you guys are going to have to sort out and recognize when you're dealing with a Chem 200 problem versus one where you're dealing with a Chem 201 problem, which you're going to need to realize that it deals with equilibrium, and you're probably going to have to think about equilibrium constants and ice tables to sort that one out. Whereas the Chem 200 problem is somewhat easier, where it's a limiting reagent problem. It reacts until something runs out. So we're going to talk about that next. Also, we're going to introduce this idea of relative acid-base strengths. So once you realize that weak acids come to equilibrium where there's a mixture of reactants and products, you can talk about one weak acid versus another weak acid. And you can talk about relative strengths. So what I'm getting at here is I can have two different weak acids. And if I have the same concentration, say 0.5 molar of both weak acids, HA and HX, just say one is hydrofluoric acid, the other one's acetic acid, they're both weak. But one of those acids one of them is going to be stronger than the other. Now, how do I know which one's stronger? You probably could guess it. I'm going to need to compare their Ks, their equilibrium constants, so I can see to what extent those reactions take place in water. So I'm going to be able to say, well, because of the equilibrium constant, this acid, HX, creates this much proton or hydronium ion, whereas the other one only creates this amount. So HX is a stronger acid than HA, but I have to watch out. I have to realize that HX is still a weak acid, even though it's stronger than another weak acid. So I have to be careful with my terminology, and I have to understand these subtle differences that make a big difference when solving these problems. Any questions on anything so far? No? Okay. No questions on anything. All right. So this gives us kind of a list of some acids that you might deal with in this class. And it tries to distinguish between those ones that are strong and therefore fully dissociate, and therefore they're limiting reagent type of problems that you face in first semester, versus the weaker acids where there's a balance between reactants and products, and you need equilibrium constants and ice tables to solve their concentrations. And so here I have a list. Here's some strong acids. Here's a bunch of weak acids. And these guys are so weak, they're spectators. Also in this list, I have conjugate base. So I see that the conjugate base differs from the weak acid by 1 proton. So an H plus is gone from the acid, and I've created the conjugate base. So you'll see that all of these guys, or a lot of these guys, are negatively charged. And it says over here that the stronger the acid or the base, the weaker the conjugate. And that's kind of an important point. And I just want to ask anybody out there what that means to them. What do you guys think?
It sounds to me like if the acid is donating proton, it's losing its strength, and vice versa with the base.
All right, good. Now listen, I think it's a lot simpler than that. And just thinking about that kind of helps you hopefully understand what I'm about to tell you. Let me just insert a new slide here. Okay, let's take a look at two acids. Let's take a look at HCl, and let's take a look at HF. Okay. Now, what type of acid is HCl?
Strong acid.
Yeah, it's definitely a strong acid, right? So I know that if I put that in water, then I can write this equilibrium, H3O plus Cl minus, but I know that it's a strong acid. I know it's 100% dissociated, and therefore I know this equilibrium lies to the right. And essentially, there's no HCl left. Okay, so another way to write that would say, okay, this arrow going this way is huge, and the one going back to the left is so microscopic you can't see it. the equilibrium lies towards product. It's a limiting reagent type of a problem. And what do I mean by that? I mean that if you have 2.5 molar HCl, well, hell, you don't have any HCl in there. What you have in this case is 2.5 molar H3O plus 2.5 molar Cl minus, right? That's what you have in this solution, 2.5 molar HCl aqueous, okay? You don't have any HCl in there. It's a strong acid. It's fully dissociated into its ions, as opposed to a weak acid, HF. Now, HF is going to form an equilibrium with its ions. And I know that for 2.5 molar HF, I'm going to have mostly 2.5 molar HF left and relatively little H3O plus. How do I know that? I know the equilibrium constant for this is around 6.6 times 10 to the minus fourth. So it's around that, 6.8, 6.6, depends on where you get your value from. But it's small. And that means that less than 5% of this guy is dissociated. So you got 95% HF in there and relatively little amounts of H3O plus. All right, so how does that tell us about the relative strength of the conjugates? And why can we use equilibrium techniques to tell us about the relative strength of the conjugates? All right, I have a strong acid, HCl, and its conjugate base is Cl minus. I have a weak acid, HF, and its conjugate base is F minus. Now, since HCl is a strong acid, I know the equilibrium lies way to the right, which makes Cl minus obviously a weak base, or I should say very weak base, because it has no strength to push that equilibrium to the left. If it was strong, then it would react with H3O plus, but it doesn't really to any extent. And I know it doesn't because the K for this, which tells me where that equilibrium lies, is about 10 to the 6 or a million. So strong acid, large K, lies to the right, and that indicates that its conjugate base is weak. It can't react very much. And it's so weak, the conjugate bases of strong acids are called spectators in Chem 200. They just don't react. As opposed to conjugate bases of weak acids, they can react a little bit because there is a equilibrium here. So the moral of the story is the stronger the acid, the weaker its conjugate base, and the weaker the weak acid, the stronger its conjugate base. And so that's all implied back here in this list of conjugate acids and bases. In fact, if I take sodium chloride and I take a solution of sodium chloride, I could stick that in my mouth. I could gargle with sodium chloride, right? If I put it in water, I know from Chem 200 and my solubility rules, I'm going to get Na plus aqueous plus Cl minus aqueous. And I know this is a base, Cl minus. It's the conjugate base of HCl. And I also know that because it's the conjugate base of a strong acid, that this equilibrium is going to lie way to the left. I'm not going to form HCl in my mouth and burn me. I'm going to know that this is pretty much a spectator. It's non-reactive. And it's not going to change the pH of any solution. I'm just not going to generate any of OH minus that's going to change the pH of water, because this base is the conjugate base of HCl, which is a strong acid. So this base here is so weak that it's a spectator. Whereas this base, F minus, is the conjugate base of a strong, of a weak acid.
Hello?
And it's going to, whoops, sorry about that. It's going to change. I kind of got lost. I was trying to mute somebody. Somebody out there needs to mute their yeah, thank you. Okay. All right, so back to this slide. Any questions on this? Okay, so just to recap, weak acids and bases are going to be the meat and potatoes of this this chapter, but you're going to need to be able to recognize the strong acids from first semester general chemistry, so you don't apply ice table techniques to solve them, those kind of problems. You are going to just use limiting reagent techniques. Also, this slide says that there's a relationship between the strengths of conjugates, and they're inversely proportional. In fact, for the strong cases, their conjugates are so weak, they're spectators. All right. So if there's any questions, just let me know. This next slide is an important slide because it shows you what happens in the very important solvent of water, and that's where we're going to be using most of our equilibrium concepts. We're going to be taking most of our problems from equilibrium that are going to be of the aqueous type, so it involves the solvent of water. So you have water in there in the majority, and it's in the background. So we should really first start off with the discussion of the equilibrium of water. And that's done by recognizing the auto-ionization of water. So in this slide, I have depicted here that there's two waters that can react with each other. And in that reaction, I form hydronium, or an acid, and I form this hydroxide base. That's called the auto-ionization of water. Now, you can drink water, you can swim in it, and so forth. So what does that indicate to you about the concentration of H3O plus and OH minus? Is it big or small?
Very small.
Yeah, it's going to be very small. So what does that tell you about the K for this reaction?
It's small.
Yeah, it's going to be very small. All right, so there's the autoionization of water. We use the law of mass action to define the equilibrium constant Kc. And I see it's the concentration of the products to their stoichiometric coefficients over the reactants to theirs, H2O squared. And I also noticed that this is a pure liquid. Its concentration doesn't change much. It's 55 molar. So I can take that constant concentration, incorporate it into Kc, and what I get is what's called Kw. And Kw is what you'll find in reference manuals. That's the equilibrium constant for the autoionization of water. And you see that in fact it is very small, just like you guessed it would be at 25 degrees. All right, so one of the things that you can do right now that we know what the equilibrium constant is for the autoionization of water, you should be able to find out using your equilibrium techniques what the concentrations are of hydronium and hydroxide. So what I want to do next is to show you how you would do that. And you're going to see this and say, oh yeah, I understand because I know how to do it equilibrium in ice tables. So I just write for the autoionization of water, then I have initial change equilibrium. Now, since this is a pure liquid, it doesn't enter into the definition of the equilibrium constant, which we call Kw, right? Kw just equals H3O plus times OH minus. So we don't have to keep track of the concentration of water. It's already in the equilibrium constant. So in the ice table, I can just put a dash here because it's not applicable. Now, if I have pure water, like deionized water or distilled water that you might find in the lab, then I can imagine initially that it was just H2O, then it comes to equilibrium, and I get some algebraic parameter, which is plus. So I see that Kw equals x squared. It also equals 1.4 times, no, sorry, not 1.4, just 1 times 10 to the minus 14th. Okay, so I can solve for x. It's the square root of that, and I find that x equals 1 times 10 to the minus 7 molar in pure water. And so that's why you can swim in it and you could drink it and stuff like that, because there's hardly any, very little bit of hydronium or hydroxide in pure water. You wouldn't want to drink it though all the time, because we humans are animals and we evolved drinking natural water like rainwater, and it has ions in it. And that's why when you go to 7-Eleven or wherever to buy some drink to refresh you, it has electrolytes. And natural water has lots of ions that are dissolved in it. So that's what you really want to drink. Also, if you're in an electrical storm, you don't want to be standing in rainwater because it has lots of ions in it also, and that can carry electricity. Pure water is not a good conductor. It doesn't have a lot of ions in it, so it doesn't carry electricity very well. So that's something to keep in mind. Now, I have the concentrations of my hydronium and hydroxide. And so now it's a good time to introduce the P anything PY formalism. I don't know. I'm just PY equals minus the log of Y. It's P anything equals minus the log of that thing. This is defined function. Some graduate student probably did it because they didn't want to talk about concentrations and powers of 10. They just wanted to reduce it to whole numbers. So we can define what's called the pH, which is minus the log of H plus or H3O plus. Or I can say pKw, which is minus the log of Kw. Now, I know what Kw is. It's 1 times 10 to the minus 14. So I know that pKw equals 14. Now, how do I know that? It's the same way I know that the pH of a solution that has an H plus concentration is 7, because pH equals minus the log of the H plus concentration, which equals, well, the log of 1 is 0 plus the log of 10 to the 7. So I got minus the log of 10 to the minus 7. And I noticed that the log base 10 is the anti-function of 10 to the whatever. So those two wipe out each other. And I get minus a minus 7, which equals 7. So there you got it. You have the autoionization of water with a Kw of 1 times 10 to the minus 14th, which tells me that the pH of that solution is going to be 7. And the pOH is also going to be 7, as you could figure out. And because of this analysis, that analogy right there, we can say that the pKw equals the pH plus the pOH. And I can derive that using the law of logs, which just says that the log of x times y equals the log of x plus the log of y. I can show you that if anybody is interested, or we could just go on and you could look it up. So no one's interested? 5, 4, 3, 2, 1. All right, so we'll move on then. So we have all these analogies and mathematical equations that we're introducing and that you guys will have to work with. In this slide, we mentioned that the common pH range is 0 to 14, but there's no rules on possible pHs. In fact, in some situations, like 2 molar HCl, you can have a pH that's negative. And there's no reason why you can't have a pH that's above 14. This is just most of the common compounds and things that we find around are in that range from 0 to 14. And here are some of those common acids and bases that you might find around the house and so forth. Okay. This slide here talks about some of the stuff that we already talked about with the pKw and the definition of P anything equals minus the log of that thing. And so you'll be seeing this in terms of P times equilibrium constants, or pH, or POH, and so forth. All righty, moving right along. Now, how do we measure pH? The easiest and probably the most accurate way to measure pH is with a pH meter. But that depends on how good that pH meter is. And pH meters can cost, if you have research grade pH meters, they could cost, $20,000 or more. The pH probes that we have in Chem 201 lab, they usually only cost $100. So they're not that expensive, but they're not that precise either. And the accuracy is only good within the range that it's standardized, and so that can change. So if you have a pH meter, then that's a good way to go if it's pretty good. Otherwise, a more chemically interesting way to find the pH of a solution is using indicators. And so that's what we do a lot of the times. And here are some representative indicators that are found in the lab. These compounds are usually very large organic hydrocarbon compounds with rings in them that have maybe a hydrogen that can be lost. So they're kind of like acids. So when a base concentration gets up to a certain point, it gives up a proton, for example, and it may change color from the acidic color to now the basic color after it gave up that proton. And you can read down that list. I think you'll see one that you recognize down here, which is the phenolphthalein. And in the first lab that you guys are coming to school in the lab and doing, deals with a phenolphthalein indicating an endpoint to an acid-base titration. That titration is between sodium hydroxide, which is in the burette, and your unknown acid, which is dissolved in a flask. And you bring that to endpoint. And I asked the other day in my lab what that meant, and someone said, it's when the solution's neutralized. And I said, okay, so if that's true, the pH is 7, right? And they're like, yeah, okay, that's 7. But that's not always true. Furthermore, check this out. Phenolphthalein goes from colorless to red at a pH of 8.0 to 9.8, and it's not near 7. So the question that I often ask my students is, using phenolphthalein, does that introduce error in your experiment for finding the endpoint, which is an approximation to the equivalence point between an acid and a base? So you can relate the moles of what you know of one reactant, the acid or the base, to the other to find out what you want to know. And that's essentially what titrations do, and phenolphthalein is often used. So what do you think about that, guys? Do you think that using phenolphthalein might introduce an error into your titrations? No?
Not as long as you know the difference between the endpoint and the equivalence point.
Yeah, that's true. Yeah. It's even simpler than that, though. When we get to titrations in a little bit, we're going to see that this doesn't introduce any error in your determination, even though it doesn't change color until a pH of 8. So we'll just keep that in the back of our minds, and we'll get back to that later when we study titrations in the next chapter. Okay, so I was telling you before that you're going to have to be able to distinguish between strong acids and weak ones, for example, because the strong acids, you're going to use limiting reagent techniques to solve, for example, pH, whereas for weak acids, you're going to have to apply an ice table approach. So how are we going to do this in Chem 201? The easiest way is to say, hey, listen, just memorize these 7 strong acids and assume that any other acid that you deal with is going to be weak. And there's other strong acids, and your book gives examples of how to recognize those, but we're going to take the simple way out and just say, if it's one of these 7 strong acids, then you can use limiting reagent techniques. If it's another acid not on this list, then you can assume that it's weak and comes to equilibrium. Okay. So you guys don't really have to memorize these. You can put them on a little 3x5 card or something and then look at it when you're taking the exam or doing your homework. But I find if you do enough problems, you're going to end up memorizing them anyway. So let's take a look at them. Essentially, it's the 3 halogens without HF, right? So we got HCl, HBr, and HI. They're all strong. HF is weak. Does anybody know why HF is weak compared to these guys? HF, there's HCl, HBr, and HI.
Does it have to do with ionization energy?
Yeah, it has to do with the bond strength. Because the longer the bond, the weaker that is, the easier it is to break. And that's the realization of this becoming an acid, right? So the weaker the bond, the stronger the acid. This bond for HF is pretty strong. So it's a weak acid and not a strong acid. So that's how the argument goes. And you could think about it in terms of what you know from Chem 200 as far as atom size. So I have H is about this big, and then F is about that big. Then Cl is going to be a little bigger than I, and Br is bigger. So you can see that the radius each time is going to get larger as we go down that group. And so since the radius is larger, the bond length's longer, it's weaker and easier to break. And so the strength of the acid increases as you go down the halogens, down that column. All right. What else do we have? We got the halogens, then we have nitric, chloric, perchloric, and sulfuric. Okay, so remember, these are the oxo acids, and so they have a different name, nomenclature than the hydro acids, like hydrochloric, we know as HCl, but chloric acid is HClO3 because that comes from chlorate. So 8 goes to ic acids, so it's chloric acid. One more oxygen is perchloric chloric acid. Okay, so those two. The other two in that list is chlorus, HClO2, and hypochlorous, HClO. Guess what kind of acids these guys are? Well, if they're not
acids?
strong, yeah, correct. They're weak. So they're weak. So these are the 7 that you guys should memorize, or at least write down on a 3x5 card or something close so you can use as a reference. And so whenever you have a problem dealing with these, you know that the acids are strong and the deprotonation is complete 100%. Now, having said that, I should probably talk a little bit about sulfuric acid, which is in this list. What makes that different from all the others? Anybody know? All right, I take that as no. The difference is it has 2 protons. All the other ones are monoprotic, only 1 hydrogen. So sulfuric acid has 2. And when you were in Chem 200, you recognized that as a strong acid. But was that really correct? In other words, you said H2SO4 plus water, or I could just get rid of that and put aqueous here. Go like that. 2H plus SO4 2 minus, right? I can say that. And I can even say that this is, well, not really in equilibrium, but it goes to completion. And that's what you guys did in Chem 200. Now, was that correct to do that? The answer is yes and no. How you like that? That's why chemistry is so interesting and people hate it so much. Now, for the first proton, it's yes. That goes to completion 100%. So that's Chem 200. But now this guy right here, this is what we call, remember, amphoteric? It can act as an acid or a base. It can act as a base if it accepts a proton. But remember, it's the conjugate base of a strong acid. So it's really, really weak, so weak. You know what we call it?
A spectator.
Yeah, it's called a spectator. So you don't have to worry about it being the conjugate base. It's too weak. It's a spectator. But it can act also as an acid. And this guy is a weak acid with an equilibrium, and it has an equilibrium constant. I don't know what it is offhand, but I know that it's 10 to the minus something. I don't know what. It's small. Okay. So this is where Chem 201 ice tables are going to come in handy for solving how much proton you'd expect from any dissociation of this amphoteric conjugate base to produce more acid. You're going to need to know something about the K. So for sulfuric acid, the moral of the story is the first proton's strong, the second one's weak. So you get a combination of both worlds with sulfuric acid. All right, moving right along, we have the identification of strong bases, because we're going to need to know them from weak bases, because we're going to need to know when limiting reagent techniques from Chem 200 should be applied and when equilibrium techniques from 201 should be applied. So for strong bases, it's a lot easier to recognize those guys. And you can see it's pretty much any metal, usually group 1 or 2, sodium, potassium, lithium, and a hydroxide. You know from your solubility rules that they completely dissociate. So I have sodium hydroxide in water goes to Na plus OH minus. And this is really not an equilibrium that goes in the back direction. It's pretty much to completion. So again, this is 100% ionized, and that's what constitutes a strong base. Okay, so if I said I have 1 molar sodium hydroxide, I don't have any sodium hydroxide in that beaker. It's all Na plus and OH minus, because it's a strong base. And so I know I can recognize those as metals plus hydroxides. Now there's other strong bases that can exist as well, and they can generate a concentration of hydroxides. But in Chem 201, we don't usually look at these guys so much. We stick to the metal hydroxides. So if we're recognizing strong bases, it's a lot easier, I think, than the strong acids case. All right. This slide introduces our next equilibrium constant, and it's called Ka, and it applies to any weak acid. So this is some generic weak acid. We could call it HA or HX. You can think of something like hydrofluoric acid, HF, or acetic acid, or citric acid, or one of the million other weak acids. How do I know it's going to be a weak acid? A few things tell me that it's going to be a weak acid. One, it's not one of the 7 strong. 2, I can look at this value for the equilibrium constant and see that it's going to be small. It's not an equilibrium constant for a strong acid, it's for a weak one. So it's going to be 10 to the minus, I don't know, anywhere from -1 to minus 10, usually in that range. And so let's take a look at how this equilibrium constant's defined. Now I have the reaction between some weak acid and water to form the conjugate acid hydronium and the conjugate base A minus. And like I said, if this was HF, that would be F minus here, just to put a face on that. I know I can form Kc for this reaction. According to the law of mass action, concentration of the products to their stoichiometric coefficients over the reactants to theirs, but I know water, its concentration is constant, and so I can incorporate it into K, multiply both sides by 55, and what I get is Ka. And that's what you're going to find in your textbook or any reference manuals. You're going to find Kas for weak acids, and they're not going to include the water specifically in that expression because it's already in the equilibrium constant value. All right, any questions on that? So this
Is it safe to assume that pure water is always 55 molar?
Yes. Yeah. So that's just the concentration is the density over the molar mass. And so that doesn't change. The density, oh, I should mention that it's temperature dependent. I didn't have anything here, but you know all equilibrium constants are temperature dependent. So this is at 25 degrees Celsius. That will change with temperature because the density changes. So the concentration of water is the molar mass divided by, the density divided by the molar mass. And so what changes is not the molar mass, it's the density with temperature. All righty. So yeah, we say that the pH of water is 7, but that's only at 25 degrees where the equilibrium constant Kw equals 1 times 10 to the minus 14. If we change the temperature, then that equilibrium constant changes and the pH changes. All right, so thanks for asking that question. Any other questions or comments? Okay. All right. This slide here is pretty nice because it gives you a list of weak acids. And if I didn't have that name up here, weak acid, how would I know that these are all weak acids? Does anybody see it on this table? How would you know all these are weak acids?
Is it because the small Kas?
Exactly. So that's how you would determine, or that would be a tip-off that these are all weak because they have Kas that are all 10 to the minus something, whereas a strong acid would not have a Ka because you're going to assume that it's so big, like a million or more, that it's 100% dissociated. All right, what's another nice thing about this slide is that it shows you which of the protons are going to be lost, which are the acidic protons. So for HF, there's only one. That's a no-brainer. Nitrous, there's only one. But then you get the benzoic acid. There's 6 hydrogens on there, but only one is acidic, and it tells you which one is acidic. Benzoic acid is in the category of carboxylic acids, and all carboxylic acids like benzoic acid, acetic acid, propanoic acid, they all have this characteristic COOH group, or the Couch group. They have 2 oxygens in this group, which are highly electronegative and pull electrons towards it and allow it to accept that extra electron that's left behind when H plus leaves. Now, the other hydrogens are not depicted on here because it's using some organic formalism for this structure. But in this structure, I have a carbon here, 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 and here, and there's a double bond between those two, and then a single, double, single. But each one of these carbons makes 4 bonds, so there's a hydrogen off of each one. And these hydrogens are the hydrocarbon bonded ones, hydrogen to carbon. And those guys are pretty strong. That carbon hydrogen bond's pretty strong, and you don't easily lose hydrogens from those positions. So you have to realize that too. Again, for this acetic acid, I have the acidic hydrogen, and then I have those carbon hydrogens over here that are not lost because they make strong bonds. They're not acidic. So even though it has more hydrogens in the molecule, these guys are all single deprotonation acids, or just one hydrogen is being lost as a part of being an acid. Okay, so what else do we have? I have a whole list of Kas. So I'm going to ask you to look at that list of Ka and pick out in that list the weakest of all the acids, of these weak acids. See if you can pick out the weakest one.
Hydrocyanic.
Hydrocyanic, that's a good guess, but not quite. Because I have 4.9 versus 1.3. So which one of those is going to be the biggest? You guys still with me?
Would it be phenyl?
Yeah, it's going to be the last one. That's going to be the smallest. And you're right. So this has the smallest Ka, and therefore is the weakest acid, right? It's a little smaller than this one. Okay, good. So which one's the strongest acid in the list?
Hydrofluoric acid?
Correct, because it has the largest. Is hydrofluoric a strong acid?
No.
No, it's not. It's just the strongest one in this list. They're all weak, though. All right, great. Now, I'm going to ask you one more question before we break our discussion, and that is, out of all the conjugate bases in this list, which one is the strongest conjugate base?
Would it be phenol?
Yes, it's the phenolate anion down here. This guy's the strongest because of what we said before. The strength of the conjugate is inversely proportional to that of the acid or the base. In this case, it's the acid. So the weakest acid gives a base that has the strongest strength in this list. So this is going to be a stronger base than any of these other guys. Okay. All right. Any questions on anything before we break? Then this is a good time to stop till tomorrow. We'll pick it up. We'll do a little recap and go on from here. And I'm just going to hang out in case anybody has any questions they want to go over something. But thanks for coming and asking questions.
Thank you.
Yep. See you guys.